Hey everybody, it's Tony from Adafruit, and this is part 3 of the Raspberry Pi Talking to Wi-Fi Things series. So in the first two parts, we kind of looked at some simple ways to have a little Wi-Fi microcontroller like the ESP8266 send data to a Raspberry Pi. And I showed some simple little commands using a tool called Mqtt, where you can basically receive data that's sent over a socket connection. And then in the last video in part 2, we looked at how to have a Raspberry Pi send commands to the ESP8266 board, so like turn an LED on and off, and again you could use Mqtt to do that. So in this part 3 video I thought, well, let's put it all together and let's build something that has some Python code running on the Raspberry Pi that listens for socket commands, could turn on an LED, turn it off, something like that, and then also have that Raspberry Pi code send commands to an ESP8266 board. So let's just kind of dive in. I'll show an example first of what we're going to build, and then we'll go through kind of the code of how we modify the previous example to build on top of it, and really show how to do some basic Python socket programming with the ESP8266. So let's just kind of dive in. We'll jump to the main view right here. Let's see. We'll go here. And so I've got it kind of running right now, the finished project here, and then I'll kind of walk through it. And so up in the top right up here is the Raspberry Pi, and so this has basically connected to the Pi. I have a little push button right here, and then up above is a green LED. And then over here is the ESP8266 board. So this is the Feather Huzzah ESP8266. Real nice little Wi-Fi microcontroller. I've used it in the last two parts of this series. And by the way, too, when this goes up on YouTube, look in the description below, and I'll have links to the previous videos and any links that I show, any web pages and stuff. You can find them down there. But that's the Feather Huzzah, and it's connected also to a push button right here and a little LED. Now watch what happens. I'm going to press the push button on the Feather Huzzah, and look at that, the light on the Raspberry Pi turned on, and I can do the same thing. I'll press this and it's turning on the light over here, or turning it off. And same thing happens on the Pi. So I press this button and you see the red light on the ESP8266 turns on, and I press it again and it turns off. So that's pretty cool. I mean, I can just kind of press all these, mess around, kind of press them both at the same time. And so what's happening here is whenever a button is pressed, like on the ESP8266, it's connecting to the Raspberry Pi over a little socket connection. So it's using the network, and the ESP is connected to my Wi-Fi network. So it connects to the Raspberry Pi, and it sends it a little command that tells it to toggle the LED on and off. And you can see in the output here, this black terminal, this is from the Raspberry Pi, so I have a little server script running on there right now. And then this is from the ESP8266, so this is the serial output. And they both just kind of print out, as they change. But it's pretty cool. I mean, the exact same thing is happening on the Raspberry Pi, where I press the button and then it will actually connect to the ESP8266 and send it a little LED toggle command that'll turn on or off the LED over there. So real cool, good example of two-way communication between these two devices. It looks kind of basic, but that's really all you need when you have two different devices that want to talk to each other. You can build on top of this and have all kinds of advanced stuff, like have sensor data being sent and maybe commands being sent from the Raspberry Pi. So let's just kind of dive in, and we'll get started, and we'll just kind of iteratively build on this as we go, and just start simple and kind of build on top. So what I wanted to start with maybe first was on the ESP8266 side. Let's change it a little bit. So this is the code from the previous video, from part 2, where it's basically listening for an LED on and an LED off command, and if it gets those, then it just turns its LED on or off. So I was thinking, let's change this slightly so that it listens for a toggle command. So there's just one command now, and when it gets that toggle command, then it'll just flip the LED on or off. So it's just a little bit simpler. Like, each side doesn't need to keep track of the state of the other side. The Pi doesn't need to remember, is the ESP on or off, and then send it the right command. Just send it the toggle command. Basically say, hey, whatever state you're in, flip it around, and we'll go from there for it. So to do that, it's pretty simple. We're just going to take the previous code. So we listen for a command. Remember, we use that read bytes until we look for a new line. So we read a line of text, and then we look for an on or an off command. So basically, I just want to change this. I only want to look for, how about a toggle LED command? So we'll make it all lowercase, toggle LED, and this is 10 characters long. So remember, we're using that strncmp. So go back to the previous video if you aren't really familiar with this. just to compare the strings here. And then I need to bump up the buffer size a bit, so we'll make this 11 characters long, and we'll tell it to read up to 10 bytes of data so that we can pick up this toggle LED command. And then I'm not going to do anything else with this, so like this is the only change I'll make. So let's save this sketch, and then I'm going to upload it, so make sure I have my ESP8266 selected. So and I've got all kinds of boards in here, so yep, it's selected. And then the serial port, make sure I've got the port for it, so yep, that's all good. And then I'm just going to click upload on this. And I'm going to go to my Pi right now, and I'm going to Control C just to kill the server that's listening. I'm going to move up to a different directory where I've got kind of the code that we're going to work on in progress in here. So let me switch there. And we should be just about finished uploading. So it's still compiling, so we're not there yet. And we'll just kind of let this do its thing. So it's going to upload to the ESP8266, so it's writing all the flash memory there. And like I had said, I think maybe in the first videos, you don't have to use the ESP8266 for this kind of a project. There are all kinds of little Wi-Fi microcontrollers, and maybe in a future video, like I'm thinking for this series, I'll probably do one more part. We'll do like 4 parts. I kind of like just doing 4 videos. It keeps things to like maybe 4 hours or so in total. It's something you can get through in a day. I don't want to do, days and days of video on this. But okay, so anyways, so maybe I might come back in a future video and try the other Wi-Fi microcontrollers, because we've got the AT-Wink 1500, which is a really nice Wi-Fi microcontroller from Atmel, and then the new Wicked board or WISD board, which is a really powerful Wi-Fi microcontroller. So all kinds of cool Wi-Fi boards, and I'm sure a year from now there's probably going to be like even more Wi-Fi boards to play with. But the basic ideas are all the same between them. They all have a concept of socket programming. For the classes might change slightly, but everything is pretty similar here. And one thing I forgot to do, because I'm looking at the serial output, it's trying to connect. I need to put in my wireless access point details so everyone gets to see my Wi-Fi password, which at this point maybe I shouldn't even have a password because it's all over the internet now. So okay, so there, let me save that. Let's re-upload this to the board. And again, like the previous sketch, so this is using that MDNS, that multicast DNS, to assign a really nice little name like ESP8266 thing to the board. So my Raspberry Pi doesn't need to know the IP address of my ESP board. It's going to use the multicast DNS protocol to look up that IP address just based on this host name here, this ESP8266 thing. Or it's not technically a host name, but it's really similar to it. So okay, I think we're just about done. Okay, cool, just uploaded, and now it's going to connect hopefully to my network. And yep, okay, now we're connected. Okay, so now my ESP board is running, and it's listening for that toggle_LED command. So let's go to the Pi and let's just test out. We'll use our favorite tool, Netcat, to do this. So let's echo toggle LED, and we're going to pipe that to Netcat, and we're going to do ESP8266-thing.local because that's using the multicast DNS address. And go back to the second video, the previous one we did, if you haven't seen this or you're not familiar with it. And then port 5000 is what we want to do. So I just sent that, and that's cool. So the LED just turned on, and then I'll send the same thing, and we should hopefully see. Let's see. Maybe I got something wrong here. So it said printed LED on. Oh, duh. so I changed it to listen for the toggle LED command, but I'm actually just turning the pin on. So I really want to toggle the LED now instead of turn it on. So I'll show you a really easy way to do that. You can actually just use do the Boolean not, like negate or invert. So if it's a true value, make it false, or if it's false value, make it true. Do the inverse of a digital read on the LED pin. So even though the LED pin isn't set up as an input, you can actually technically read it like this to see kind of what's the current state, and then this exclamation point says invert whatever state you are. So if it's true, if it's at a high level, then it's going to invert that and set it to a low level. So real easy little one-liner that you can do to toggle the pin state. And actually I probably should change, let's say toggled LED, which doesn't really matter. We'll let it upload as is. It's just going to print out that turn the LED on when it's actually toggling it. Okay, so we'll let this thing finish here in a second, and then we'll test it out, and it should work now. So again, I'm just going to use the netcat command. And I like to, break things apart into simple little things like this. Make a small change, test it out from the Pi. because as you get into socket and network programming, it's really easy to, get really deep into something and then realize that maybe there are bugs and things, and it's really hard to test it because you've got like 2 devices, and it's sometimes hard to simulate network traffic. And so, break things apart, test everything in isolation or as isolated as you can, and then build on top of that. So, okay, so that uploaded. Now let's try this again. So we toggle it on and we toggle it off. Okay, cool. So we're all good there. And let's see. Oh, that's interesting. I just did the command. There we go. Okay, so it took it a second. Maybe my Pi maybe had to look up the IP address again. So, sometimes can take a little bit longer when you've got network stuff involved. So, okay, so that's cool. Now let's write some code on the Raspberry Pi to basically listen for a button press and then send that toggle LED command over to the ESP8266. So let's see, I'm going to look at the Raspberry Pi. So I'm connected to my Pi in this text editor right here. So I'm using this little tool called Mac Fusion that I've talked about before that lets you mount your Raspberry Pi as an SSH file system. So I've got this all set up, and I'm going to create a new folder, and let's call this Python, oops, let me highlight that, Python 3 underscore server. So I was thinking, let's do this in Python 3 because it's actually not that different from Python 2. And just in general, going forward, I'd like to start using Python 3. It's 2016. It's time to start making the switch over. And there's one small difference I'll mention with the socket programming that we're doing. Like, they renamed some of the socket classes, but otherwise, the difference between socket programming in Python 2 and 3 is pretty much negligible. There aren't a lot of big differences. So, okay, so inside of here, and then let's make a new file, and let's call this server.py, because eventually this will be a server. But for now, we're just going to have it, listen for these button presses, and then we'll build on top of that as we go. So, okay, so to listen to a button, I need to import the rpi.gpio class. This is the one that pretty much everyone uses to talk to GPIO on the Raspberry Pi. And then I'm going to do if name equals main. So this is kind of the convention in Python for when you want a block of code to run when you run your Python script. Like, you don't have to have this, and then your code is always going to run. It's just a nice thing to do so that, like, if you define classes and things inside of here, another Python script can import this script, and it won't actually run this block of code, because this name variable kind of means, like, if I remember correctly, it's like the context of where this thing's running. So you see this a lot. This is kind of, think of this like, if you're used to C programming, like the int main function, like the entry point for your code is what this kind of effectively does. So, and then in here, it's, pretty much, I'm just going to have a loop. So just loop forever, listening for this button press. But maybe before I get into that loop, I need to do a little bit of setup with the RPI GPIO library. So you have to do the set mode function to the BCM pin numbering. This is just, you can do either the board numbering or the BCM numbering. I usually use the BCM numbering because that's what the PyCobbler shows on there, all the pin numbers. And then let's do gpio.setup. So here we can set up our LED on the Pi and our button as an input. So for now, maybe we'll just start with the button. And maybe before I get too far into this, let's define the button pin as a nice little variable at the top. And so my button is connected to pin 23. And the way I have both of these buttons set up, basically, so this is a momentary push button. When you press it down, it connects one side to the other side. And what I do is on the Raspberry Pi and on the ESP8266, I have one of the halves of the button connected to an input. And that input I've configured to have a pull-up resistor, so that if nothing is pulling this to a ground value, then it's naturally just going to stay at a high logic level. And then the other side of the button I have connected to ground. So when you press the button, it's going to connect ground to that input. It's going to pull that input down to a low logic level. And then at that point, you can read, like, okay, if it's false, if it's a low logic level, then your button is pressed at that point. So exact same thing on the ESP. One half of the button is connected to an input that's set up as an input with a pull-up resistor, and then the other half is connected to ground. So real common way to use a button, momentary button like this. So okay, so then let's set up our button pin, and let's make this an input. And then the little magic thing you need to do with RPI GPIO to set a pull-up resistor, and I'll just go to their examples here. So basically in the inputs page, and I'll put a link in the description below to this, you basically want this little pull-up down keyword argument to be specified. So this tells it to set a pull-up resistor. And the cool thing on the Pi, you can do a pull-down resistor if you want to for this. So this way, naturally this button is always going to read at a high logic level until I press it and connect it to ground, and then it's going to read at a low logic level. So okay, so I've set that up, so that's all good. Now in my main loop, I just need to look for that button press, and the easiest way to do that, I think, is to look for when it transitions from a high logic level down to a low logic level. So that means, you've pressed the button. You could also look, if you wanted, for when it goes from a low logic level up to a high logic level, and that way you're looking for when you release the button, so you see that change. Because you probably don't want to look at, if it's low, if it's at a low logic level, because, as long as I'm holding that button down, that's going to be true. And if I had a bunch of logic associated with that, it's just going to repeat that over and over and over again. And maybe I don't really want that. So, when you want to just do something once when a button is pressed, look for that change in state. Think of it like a waveform where it goes from high to low, and you want to look for that little change, that transition to run your logic. And a real simple, easy way to do that is to just take two samples. So read your button input, wait a short period of time, and then read your button input again. And so that way then you can compare and see, okay, if the button changed during that period of time, if it went from a high to a low level, then I know it was pressed. And because I don't have much else happening in my code, I'm just in this while true loop, most of the time my code is going to be waiting in this little delay between those button presses. So, it's very rare that I would miss a button press because my code's not really doing anything except waiting for, the button press to change effectively. So, this is one way to do it. There are lots of other ways you could read a button like this. And actually the Gpio library, you can set up a pin change interrupt. I think I've used this in different videos where you can actually have it, you can give it a callback function that it will call whenever it sees the button transition from like a high to a low level. But I figured I'm just going to keep it simple here, and we'll do it this way. But there are lots of ways you can do this. So okay, so let's take a maybe first button reading, and so we want to do gpio.input on our button pin, and then I want to delay for a short period of time. So I need to import the time library, and let's do a time.sleep for 0.02 seconds. So this would be 20 milliseconds. And this is effectively like a debounce time. So, I take one reading, wait a little while. If during that period of time the signal changes, then I'll pick that up. And, you can tune this, you can tweak this however you want. You can make this pretty short. You can make this, maybe 10 milliseconds or so. But 20 milliseconds is a pretty good value for this. So then I'll take a second reading, and we'll do gpio.input, my button pin. And then, okay, now at this point, so I have my two readings, and I want to check and see if button first is high, at a high level. So that means, nothing's pressed the button yet. And my button second, so after a short period of time when I took a second reading, if that's at a low level, then I know that my change has happened. My fingers pressed the button down and it's pulled it down to a low level. And let's just print out, button pressed, just to test that this works. So, okay, so that's easy. And then I'll go back to my Pi. And also, by the way, too, and I'll put a link to the Github repository that has the code for this example, all of the code that I'm writing here. And it mentions also in that Github repository, actually I should go to it right now, I have a little bit of a README that says some setup you need to do. So there's some installation. So this explains, here's how you want to connect things up to your Raspberry Pi and your ESP8266. And then because I'm using Python 3, there's a little bit of setup that you want to do to make this work. So basically you need to install Python 3. So to do that, you just want to sudo apt-get update. So, and I won't run that because it takes a little while on the Pi. But then you just want to do sudo apt-get install -y. That just says yes, don't ask me. Python 3, and then Python 3 -pip. And I've already got these installed, so this will just kind of fail out. It won't really fail, it'll just say it's already there. And then I need to install, because remember Python 3 has separate libraries from Python 2. I need to use sudo pip3, the Python 3 package manager, install rpi.gpio. So this installs the RPI GPIO library for Python 3, which unfortunately on the Pi, because Python 3 is not installed, this library is not installed for Python 3. It is installed for Python 2, but I figured, let's start using Python 3. So okay, after you do that, then you're good to go. If you didn't do this, then your code would fail right here when it tries to import the RPIO GPIO library. So just a little gotcha there. Okay, so now let's see. So I've got let's go to my Python 3 server directory, and now let's run Python 3. So don't use Python, use Python 3, because I want to use the Python version 3 interpreter, and then that server.py script. So this is going to run, and it should just be listening for button presses. So I press this, and yep, it looks like it works. So I pressed it, and even though I'm holding it down, it's not repeating over and over button pressed. It's just looking for that transition. So okay, so that's cool. So we can detect our button presses. So now let's actually add some socket code in here. So let's connect to our ESP8266 and send it that toggle LED command, just like we did with Netcat. Now you could, if you really wanted, if you didn't want to mess with socket programming, you could just call the Netcat command from your Python script. So there's the whole sub-process module. That's perfectly valid. I mean, there's no, necessarily bad reason or no reason, why you wouldn't want to do that. But for this, I wanted to get in and get my hands dirty with some socket programming in Python. So that's what I'll show here. Now there's some good info, and I'll put links again in the description below. So there's a socket programming how-to that's actually in the official Python documentation. And it's great. It's good to read this to give you just a little bit of an overview. You'll get an idea of some of the terminology and like what sockets are. It's not going to be like a college course on network programming. You're not going to know all the differences, but it gives you a good taste. And I think this is really cool and a good thing to at least skim over and just kind of read to get an idea of what sockets are all about in Python. And then there's also the socket library in Python, or module. And this has, the reference as far as how to use the module. And so we'll use this a little bit to use the socket classes. So to get started, so I need to import that socket module. So let's add that to the top. And then, so after I press my button, so now I want to send a toggle LED command to the ESP8266. And to do that, so I need to create a socket object. And then after you create a socket, so kind of like the programming how-to here mentions, so you create a socket object and you pass in the type of socket you want to create. So this AFINet, this kind of tells you that you want to make an internet socket or like a TCP socket. There are different types, so like there are Unix sockets that are kind of like internal sockets where one process on the Pi could talk to another process on the Pi, and it kind of feels like you're writing networking code, because effectively you are. Like those two processes are pretty much completely separate. They don't share any memory, so the only way they can talk to each other is through like a socket. Now they could also just expose the socket interface themselves, a network interface, and talk through that. So it's same kind of code, and that's the cool thing about socket programming in Unix, is that it's a very low level kind of system for communication, but you can use it in different ways. So you can talk to TCP sockets or UDP sockets or Unix sockets, internal things, and it's all using the same APIs and same functions and things, just slightly different in how you create them. But we're just going to use this default that they have. So this is how you create a TCP socket, and a socket by default, it's not like a necessarily a listening socket or a sending socket. You basically explicitly have to either listen for things to connect to it or connect to something and send data. And so that's what this connect function does, is that it will connect to another device. So given like the address of the device, this gives a nice little friendly host name or DNS name. You could put like an IP address in here. And then the port is also what you need to specify. So the socket's gonna go and try and open that connection to that device. And then once you have a connection open with the socket, so the rest of this kind of mentions this is how you listen to a connection, and we're not actually going to look at this here, but you can go down to the using a socket, and there are a lot of different things you can do, but basically the socket itself has a send function on it, and so this will send a string of bytes across the socket. And then it also has some receive functions on it where you can like wait for data to be sent to you. And the socket class actually has a better reference of this, I think, than the little how-to there. So if we look at like the functions on here, so you can create a socket. This tells you a little bit more about it. And then if I go down to the actual socket class, the socket object here, you'll see this is all of the functions you can call. Once you have a connected socket, you can call these functions. And the one that I care about is the send function. And there are actually a couple different send functions. So there's a basic send function that you just throw a string of bytes at, and it'll go and send those bytes to the connected device. Now, because there's network programming involved here, there's a lot of buffering. So this send might not actually return once all those bytes have been sent. Like it won't necessarily wait for all those bytes to go out on the wire. It's actually just going to queue them up, and then internally the operating system is going to go and send those bytes out. But there is a nice function called send all, which it's named a little weird, but basically it's exactly like send. You send it a string of bytes, but it will wait until those bytes have been sent out across the wire. And so this is actually what I want to use, because I want to just blast out a command and make sure it gets sent to the ESP and then move on. This send function is good for if you're doing a lot of other things and you just want to like start sending data but then maybe move on to go do some other processing. You can come back later and check like, okay, am I done sending my data yet? But I don't want to worry about that yet. And there's a whole asynchronous side of socket programming that I'm not going to get into in this stream, but it's basically I'm using blocking socket calls, which means that for the most part, when you call send all, it's going to wait for all that data to be sent, and then the function call is going to return to you. So it lets you write code that's a little simpler, because you can say, okay, send a command to the ESP, and then once that command finishes, then the command below it will start running. So if I was doing non-blocking sockets, it's what it's called, you don't have that luxury. So like your send all command will queue up those bytes and then immediately return. And so now you've got in your own code, either you don't care and you're just going to let it send in the background, or maybe you need to wait for that to finish. And so there's a whole set of kind of APIs and things to call to look at to see like, is it done sending? Is it done sending? And then, okay, now it's done sending, and then I can move on and do other stuff. So that, there are good reasons why you'd want to use non-blocking, because you're doing a lot of things at once and you don't want to wait for one thing to finish for another thing to start. But then your code gets a lot more complex. So, it's something that I don't want to get into just yet. But okay, so that's basically all I need to do is really just create the socket, connect to it, and then call this send all function to blast out the data. So let's do that. Now, I'm going to create my socket using a context manager, which is, it's a fancy little thing in Python that lets you, normally you would use this when you're like opening a file. So you use with and then open, and you open up a file, and then you have code inside of this context manager that'll run. And then whenever that code exits, so whether it finishes and it gets to the end, or maybe something throws an exception and blasts you out of that section of code, this context manager will always ensure that the thing you created is gracefully closed. And in the case of a socket, it'll close that socket connection. Because a socket connection is kind of like a file. Like you want to make sure that you close it when you're done with it. At some point your operating system will realize that okay, your program's not running anymore, so it's going to close that socket connection. But it's smart to do these things as graceful as you can, so that you don't leave connections open and hanging if you don't have to. So okay, so let's just copy out from the little how-to here the socket create command. So we want to create the socket object, and I'm just going to copy out exactly what they have. So I'm going to put it in this context manager, and then I need to create a object that's going to be assigned this socket when it's created. So we'll just call it ESP8266. And now inside of a new indented block, I'm going to put code that runs. So after it's created this socket. So now I want to do the connect. Oops, not on the socket module. I want to do it on my ESP8266 socket object. So I want to call connect. And connect takes a tuple of 2 values. So I want to pass in the host name to connect to. And actually, let's make these a little variable at the top. So we'll say my ESP8266 name equals ESP8266 thing.local. So that's the MDNS, the multicast DNS name. And let's say, we're going to say server port equals 5000. So my ESP code is listening on port 5000. So I'm just going to have that as a little defined. And so it's basically, I need to pass first the address, so my ESP8266 name. And the cool thing is, even though that's multicast DNS, these socket APIs don't care about that. It's actually the operating system internally that is realizing that, oh, this is a .local address, and I need to do a special multicast DNS lookup to make it work. And then the port name I also need to give, so I give server port here. And you might think it's a little weird, you have to do this tuple, why aren't these just parameters? And that's just the convention with the socket programming APIs that they have. So okay, so I do the connect, and then this is going to return once it's connected, and I'm just going to do ESP8266 send all, and I'm going to do something a little weird. So because I'm using Python 3, I'm going to send a byte string. And this is just something, as I use Python 3 more, you're probably going to see more of this, because in Python 3 a big change is that all of your strings by default are Unicode. They aren't ASCII anymore. And that sometimes has some subtle differences in that, you know, a string in Python 3, like foo equals hello, is actually a string of Unicode bytes. It's not ASCII anymore. It's not, you know, raw bytes. Whereas this, if you put a B in front of this, that says make this a byte string, and this will make it an ASCII string. So it actually is interpreting raw bytes in here. So you couldn't do fancy higher order Unicode characters. You can do, if I remember correctly, like OXFF. So this would put, you know, a hex value inside of here. So it's just a subtle difference. And sometimes if you get it wrong, unfortunately, APIs and things can fail. They might say like, oh, I expected a string of bytes, but you gave me this Unicode thing and I don't know what to do. So in a lot of cases when that happens, you can switch to a byte string, and that's what I want to do here, because my ESP board doesn't know Unicode. It doesn't know how to deal with that. It really just wants ASCII characters. But I want to send it that toggle_LED command effectively on here. So, and well, actually, yeah, let's just keep it like this. So we'll do send the toggle LED, and that's it. So let's just save this. And let's run this now. So let's go back to our Pi, and we'll do our server. And now when I press this, let's see what happens. So okay, so button pressed, but I didn't see my LED turned on. So let's see if I get any output on my ESP board. So no, I don't see anything here. So let's go back and let's have our ESP print out whatever it received. Well, actually, oh, it's already doing that. So okay, yeah, so it didn't receive anything. Oh, I think I know. So I'm waiting for a new line right here, but I'm not actually sending a new line in my code. So, you know, I'm basically just sending toggle LED, but I need to actually send a new line on that so it can receive it. So let's try this. This should be what's wrong with it. Let's, but might need to do some live debugging if that's not working. So okay, so let's see. So now we've got our output from our ESP, and I press this, and we see, okay, so I got button pressed, but I don't see anything on my ESP board. So okay, let's go back and let's just test and see. Okay, yeah, so maybe something might be going wrong with our socket connection here. So let's just make sure, let's put in a print statement here. So we sent the data, and let's see if that does it. And let's cancel out of this. The other thing that might be going wrong, I can't remember if I need to flush the output of this, so maybe we might cheat in a second and look at the code that I wrote ahead of time to see how I'm doing. Okay, so I got to send the data, but it's not actually showing it here. Let's see. Let me just let's try one more thing. Let's go back to netcat and let's just double check that my ESP code is actually working. So let's echo toggle LED to ESP8266 thing.local port 5000. And okay, so that's working. So yeah, so it comes back with LED on. So okay, so something's up with this connecting. Let's see, did I get like maybe the name wrong here? ESP8266 thing.local. Now that looks okay. So okay, so let's cheat. Let's look at the code that I wrote ahead of time and see what I was doing here, because I got something wrong here. Let's see. Okay, so socket stream ESP8266. That looks okay. So, interesting. Okay, so what is wrong with what I'm doing here? Let's see, did I get maybe the name and the port wrong here? Let's see, nope, name and port look okay there. So, let's see, okay, what else could be wrong with this? And the other thing I'm trying, so in the code that that we had working before, I put in this little try finally to catch errors, and so we'll kind of see that, but it's a little weird why I'm not seeing this connect to my ESP board. So okay, well let's just kind of, let's go down the rabbit hole of debugging this a little bit more. So let's pull MDNS out of this equation. So let's just set this to the IP address of my ESP thing. So it prints it out when it loads up. So you know, let's just kind of step back and see, because you know there are lots of different layers and things that are involved here. So let's strip it back to the most basic kind of simple example here. And so okay, so when the button's pressed, then you know I'm going to create my socket object as this ESP8266. We're going to connect And let's just print out, I know this should be getting here, but we're just going to print out and say, okay, I'm connected. And then, oh, I've been staring at all. Toggled LED versus toggle LED. So this is probably what's wrong. Let's actually take this out. So it's always funny, you're streaming something like this, and and this actually happens when you're not streaming. Like, something goes wrong, and your mind immediately goes to, like, what is the most complex thing that could be broken? When in reality, it's probably a very simple mistake that I'm sure people saw ahead of time and were kind of screaming at. But it's funny how that always works, where you're so quick to jump to what you think is the most complex thing, when in reality it's probably a very simple thing. So okay, let's go back. Let's run our Python server here, and let's see what happens. So I press this, and hey, look at that, the LED went off. So that was the problem, basically. And so I pressed this, and it just sent it, and it turned on. So okay, cool. So hey, it's the simplest thing. It's a habit that I need to get better at, is looking at the obvious stuff. So I don't really need that new line, it turns out. So okay, so we'll keep it back to what it was before. Okay, cool. So this is cool. Now let's see what happens. I want to show one interesting thing. I'm going to unplug my ESP8266 board. So it's not connected. It's not listening anymore. And let's see what happens to our server. So I'm going to cancel it. I'm going to run our server again. And I'm going to press the button. And okay, so we picked up the buttons pressed, but let's see. Let's give it another second here. Because this thing's not running, there's no way a socket can be created that can connect to this thing and can actually tell it to turn this on or off. So we're just kind of waiting. And with sockets, there's there are different timeouts, so it sometimes takes a little bit of time for a call to occur. But look what happened. We just got this OS error, error 113, no route to host, and that was on this connect call right here. So it tried to connect to my ESP, but it couldn't find the device itself. It couldn't open that connection. And so that's basically a failure condition, and you need to worry about this a lot when you're doing network programming. Of you've got two different devices, they may or may not be on the network, and so they need to worry about, like, okay, if that device isn't on the network, what do I do? And with Python socket APIs, generally they'll throw exceptions when something fails. Like if it couldn't send the data, if it couldn't connect to the device, it's going to throw an exception. Now, in this case, I don't really care if this happens, because it's only when you press a button do I go into this code. So if it just so happens that you press the button and it can't connect, I want it to just continue and go back to listening for button presses, because maybe the ESP board will get turned on later and then it'll start working again. So I don't want it to completely destroy the whole program. So the easiest way to do that is just to catch that exception. So I'm going to put a try except block inside of here. Let's see, I'll remove this, sent the data, and except, and here I want to catch a certain type of exception. So I'm going to catch that OS error, which is what Python throws when the socket APIs fail. Now this is a Python 3 difference. In Python 2, there's actually a socket.error class that all of the socket errors subclass from, and they throw those. But in Python 3, it's actually the OS error. And this OS error, this is a pretty general error. So like if you open a file and it can't open it, you're going to get an OS error. So maybe I should actually do a little more logic in here to look and see, like, is this a socket related OS error? But I'm just going to keep it simple, because I only have this try except clause around my two socket functions. So if I get an OS error here, 99% of the time it should be because one of these ESP, one of these socket calls failed. So, and in this case, let's just print out, we'll say couldn't, or how about could not connect to ESP8266. And so we'll just print that out, and then I'm not going to do anything else. So the Python code is actually just going to continue running at this point. It's basically going to swallow this exception. Like if I wanted, I could raise a new exception, like maybe a runtime error or something like that. But I just want it to keep going, so I'm not going to have anything else. I'm just going to print out, and let's save that. And now let's run this again, and we'll try pressing our button. And my ESP board, it's still turned off, so it shouldn't connect. So I'm going to press the button, and it's trying to open the socket right now. And it's waiting a little while, and now we see, okay, could not connect to ESP8266. So that's good. My code is still running, so I can press the button again. It's going to try again. It's not going to work. And then what I'm going to do, so now I'm going to plug in my ESP board again, and it's pretty quick to connect, and actually you can see in the serial output it's connected already. So now let's go back and let's press our button, and look at that, it turns on. So it immediately connected and everything's working. So cool. Okay, so I think we've got half of it working so far. We've got the button on the Raspberry Pi controlling the LED on the ESP8266. So now let's go in and let's do the other half. So let's have the button on the ESP8266 send a command to tell the LED to change on the Raspberry Pi. So let's do this. Let's start from the ESP side here, and then we'll build on top of this, and I'll show you how to add some Python code to listen. So in here, let's add a few defines at the top. Let's define a button pin, because now I have a button connected to this, and my button is connected to pin 0. And then let's also define the IP address of my Raspberry Pi. So we'll say Pi address. And I've actually done ahead of time on my Pi, I've set it up with a static IP address. So when I run ifconfig, it has this 192.168.1.42. Go back to the first video in the series and I show how to do this IP static IP setup. And I do this because that's the easiest way for my ESP to know how to connect to the Raspberry Pi if I give the Pi a static IP address. As I don't think that there is a multicast DNS library for the ESP8266 that lets you do a name lookup. So like I don't think it can look up like Raspberry Pi.local on here, although I might be wrong. Maybe there is one, and maybe in a later video I could look at that. But so since I don't have multicast DNS, I'm just going to give it a static IP, which is pretty easy. It's like I know there's only going to be this one Raspberry Pi involved. So let's put in that IP address in here. And okay, so I've got a couple defines for that. Let's configure our button as an input. So we want to do pin mode, button pin as an input, input underscore pull up. So remember, I want to have the pull-up resistor so that one half of this button is connected to ground, the other half is connected to the input, and then because that input has a pull-up resistor, it's normally at a high logic level, and then when the button's pressed, it pulls it down to ground. So really easy to detect it that way. So okay, so that's easy. Now in my loop code, so right now the loop code is basically listening for a connection, like someone that wants to connect to it, and then it's parsing out the command it receives, and it's looking for that toggle LED command. So now let's add at the top our button check code, and I'm going to write it exactly how I did on the Raspberry Pi. Like take one reading, wait 20 milliseconds, take another reading. And even though I have other code in this loop, most of the time this code is going to be really quick. Like it's going to call this server.available, which is just looking to see is someone trying to connect. So that's a pretty quick call. And if no one's connected, it's immediately going to return. Like this client is going to evaluate to false, and it's going to return, and your loop's going to start again. And if I have that button check at the top of the loop, it's going to look, it's going to wait 20 milliseconds, see if there's a change in the signal. So most of the time, it's just going to be up in this first bit of code here, spinning around, waiting for the button to change. Now, when someone finally does connect, then it's going to fall through to this code here. So it's going to wait to receive all the bytes, parse out what it received, change the LED. And so during this period, the button presses won't work. I can press these as much as I want, but it's going to be waiting for bytes to be received. And I think that's okay, because this ESP board can effectively only do like one thing at once. So I'm just going to keep it simple, and while it's receiving data, it's not going to listen to button presses. So just something to be aware of, that you might not. It might not, if you're jamming on the button and things are coming in, it's not going to work. So, okay, let's do the exact same thing. So let's do button first equals digital read on my button pin, and then let's delay for 20 milliseconds, and then button second equals digital read on the button pin again. And then I want to look and see if it changes from a high to a low logic level. So if my button first equals high level, and my button second, the second reading, equals low level, then I know the button's been pressed. So we'll say button was pressed, and let's just print out serial.print line, button, make this a string, button pressed. Okay, so let's save that. And let's just upload it, again, do things in small parts. And if something doesn't work this time, I'll try to jump into, start with the simple stuff first, not diving into what might be a complex error. So, okay, let this thing upload, and then let's see what happens here. So it's just writing the flash memory, and then here's the serial output from the ESP board. So we should see it connect to the Wi-Fi network. And then in theory, the button should, when I press it, print out a message. And I'm just going to check, yeah, my button pin is 0, so right, that's what it should be. Okay, cool. So I think we're connected and we're running. I'll press the button, and okay, cool. So it detects it, button pressed. So we're all good there. Now let's just put in the code to connect to the Raspberry Pi and send the string of data that I want. So send that toggle LED command. And I'm going to make it consistent so that the ESP listens for the toggle LED command and the Raspberry Pi listens for the exact same toggle LED command. And to do this, actually, I'm going to just grab the code from the very first part in this series, so part 1, where I showed how to have the ESP send data to the Raspberry Pi. So we're just going to use exactly that code. It's the same kind of little Wi-Fi client class here. So here's the code for it, and you can see it creates a little Wi-Fi client. It calls this connect function on it, which, if you notice, is very similar to Python's socket connect APIs. It takes the host and the port. It's no surprise that all these socket APIs are very, very similar. So let's copy this out and let's put this into our code. So we will create a Wi-Fi client here, and let's, instead of calling this client, let's call this Pi. And then we're going to do if the Pi connect fails, and so here I need to specify which what's the address of the Raspberry Pi. So we want to say my Pi address variable, or define, that I set ahead of time. And then server port. So this is a define that I already had. So up at the top, so server port 5000, Pi address, IP address of my Pi. That's a static IP I set ahead of time. So okay, and then if this fails, if this returns false, then this if condition is going to be true right here. And it's going to, right now, it's going to go in and say connection failed, and it's going to wait 5 seconds. I don't really want to wait 5 seconds here, because again, I want it to be just like the Pi, where you press the button, try and connect, try and send that toggle LED command. If it fails for some reason, then just move on. Keep listening, and maybe your Pi isn't turned on right now, but if it gets turned on later, then it'll automatically work. So I'm actually just going to have it return. So this will return, and it will go back to the start of the loop again if it fails to connect. Really, I probably should, instead of returning from the function, like fall through to check if a server is connected again. But I think it's okay because it's only a 20 millisecond delay here. So it's not the end of the world if I go through another loop iteration before falling through to pick up the server or the next person connecting. So okay, so that's looking good, and let's just change the spacing. Okay, so now at this point I know I'm connected because if this failed for some reason, I would have broken out of the loop and run it again. And now I just want to send some data. So just like we saw in the code right here, there's the client.print or print line function I can use. So let's do client.print line, and I want to send toggle underscore LED as my command. And then I'm going to do the flush command that I talked about in the last stream. This just makes sure that the previous print command finishes sending. And then I'm going to do client. Oh, and sorry, I shouldn't do client. This is actually Pi is the name of the variable that I created, because it's the Wi-Fi client instance that I created and connected to right here that I want to use. So we'll say Pi, and then I want to use the close command, and so that's actually going to close the connection, or I think it's close, or no, it's actually stop, sorry, so it's the stop command. One difference, unfortunately, between I think the Python and the ESP code here. So okay, so what's going to happen here? So button pressed, it'll print it out to the serial port. It's going to try and connect to the Raspberry Pi. If that fails, it's going to retry, or it's going to go back to the start of the loop. Once it's connected, it's going to print that toggle LED command, wait to make sure that that was actually sent across the network, and then it's going to close the socket connection. So it's done. So just connects, send toggle LED, and then finish. And then it'll go on and check and see is someone trying to connect to it. So let's do this. Let's save this, and let's upload it to our board. And then what we'll do from the Pi, we'll start with netcat again, our favorite command. We'll have it listen on port 5000, and we should see hopefully that it sends these toggle LED commands when the button is pressed. So we'll let it do its thing here and finish uploading. So go. and then once it's done, we'll run the netcat command. So I think we're almost done here, and just finishing up. There we go. Okay, so we're connected. So now let's go back to our Pi, and I'm going to run way back from like the first stream, and actually the second stream I think I used it too. So the command I want to do is nc netcat -l -k. So the -l tells it to listen, -k tells it to restart. You know, like don't just listen once, listen all the time for connections. And then the port that I want to listen on, so 5000. So okay, so now my Pi is listening on port 5000, and my ESP should now send out on port 5000. So I'm going to press the button, and we see, okay, cool. So we got something here. So it sent out some bytes of data effectively here. So you know, it's printing out like I'm guessing these are the ASCII codes for the characters that I sent. And it's kind of weird why it does that, but oops, let me go back to the sketch code here. So you know, I basically printed out the toggle LED. Oh, so this is I'm not doing what I expected, and this is unfortunately a little gotcha with C and C++. You know, so basically in C and C++, single quotes mean a single character, like the character C, versus double quotes mean a string, like a null terminated string. Now in Python you can use either for a string, but in C and C++ you have to be explicit and say like this is a string. So because I had single quotes, it was actually interpreting, I'm guessing, I can't remember what it does when you have a string inside of single quotes. It's the kind of thing where it's like, man, that should really be a compile fail, because like that's a very subtle bug, as you noticed. You know, I'm getting a weird string of numbers here, everything compiled, but it's not really doing what I thought. So let's reload the code, and we should hopefully see. And this works because you know, it's not a compile error, because this print line function has a bunch of overloads where there is a perfectly valid print line for a single character. So it's using that single character print line. You know, it's doing what I'm telling it. It's just I'm not telling it what I thought I'm telling it to do right there. You know, I was telling it to send a single character, and then because I've actually sent it a string, I don't know how it's interpreting that character. You know, it's doing something crazy with that. So okay, so now I should actually be sending a real string, and we should hopefully see in here that it actually says toggle LED. So okay, I think it uploaded. It's done uploading. Yep, it's running there. So now I press this. There we go. So you see, every time I press the button, we get the toggle LED back on there. So okay, cool. Hey, and you know, maybe I planned it that way. That it's good to show simple little errors like that. So okay, cool. So we've got the Pi, or we've got the ESP sending our command over. So now the last step, I want my Raspberry Pi to listen for that toggle LED command in the Python code, and then toggle my LED when I receive that. And the way I'm going to do that, so you could write like raw socket code. Actually, you know, this socket programming how-to tells you how to create a listening socket and receive data on it. But I'm actually going to use a really nifty class that Python has, and it's in both Python 2 and 3. In Python 2, it has a different name. I think it's uppercase socket, uppercase server, whereas they just renamed it to socket server. But they have a socket server class that simplifies all the logic of listening for data, or listening for data to come in on a socket connection. And you know, it's much simpler than using just the raw socket commands. Because with the raw socket commands, you know, you have to do all the setup of like binding to a socket and listening on it, and deal with like what happens when one of those fails. There's all kinds of error conditions. And then there are the recv commands where you receive data on a socket, and you know, you don't, like when you're using those low level commands, you know, if you want to receive an entire line of data, you might only get them like a byte or two at a time, and you've got to assemble a buffer that has all that data you received, and then once you get that new line, then you can parse your buffer of data. That's a lot of code, a lot of boilerplate. So this socket server class actually does most of that for you, and it's really straightforward and easy to use. It's the kind of thing that I love about Python, where they call it batteries included, because it has libraries like this that, you know, think about like, okay, most of the time people want to write a simple socket listening class. Let's make that as easy as possible. And so this is like a basic example of how to listen to a TCP socket. So you create this little handler class that inherits from this base request handler, and it just needs to implement this handle function. and inside of the handle function, it will actually have a socket that's already been connected. Like all of the listening setup was already done for you. You just have a socket that you can call like recv and send all and send functions and things on. And there's actually an even better version of this. They have the stream request handler class where it'll give you a file-like object. So this self.r file, where now you can actually use Python's built-in read line function. So instead of just using these low-level socket recv calls, because there's no like recv until new line function, you only get that functionality once you have a file-like object in Python. So using the stream request handler, it will give you this file-like object that's actually talking to your socket. And it also has this W file member in here that you can call write on. So just like you're writing to a file. So this is pretty cool. I mean, I just need to fill in a function, and then this function will be called. So you do a little bit of setup. You create this TCP server object. You tell it what to listen on, like what port, and then you also tell it the handler class that you created up above here. And then this is actually going to go, you actually call this little serve forever function. Once you call that serve forever, it's going to go create a listening socket. And then when something connects that listening socket, it's going to call this handle function. And then you can do your logic there. You can say, okay, I want to check and see, did I receive a toggle LED command in here? So this greatly simplifies it. I just implement a function basically, and then let the socket server or the TCP server class take care of all the grunt work of, creating that socket connection, listening to it, doing all that stuff. So let's just kind of start with some of this code, and we'll pull it in. Maybe I'll start with their handler class that they have up at the top here. And actually, I'm going to use their stream request handler because that's the file-like object version that I mentioned. So let's use that because it gives us this little readline function that's a lot simpler to use. So okay, let's go into our Python code here, and let's just let's get started. So let's put that class up near the top, and I need to import the socket server module. So let's import, and actually I'm going to do from socket server import star just to import everything, so that way I don't have to prefix everything with socket server because that's kind of a long string. It makes the code a little ugly. And then let's call this my LED handler. So this is listening to that toggle LED command. So okay, so I need to fill in this handle function, and it's telling me that this self.r file is going to be a file-like object. This readline function is going to say, wait to receive an entire line of data, like something that ends with a new line character. And then the strip function, this actually just removes any white space from the beginning and end. So it'll remove the new line at the end. If I got a carriage return, it'll remove that. So it's a good thing to call just to get like a clean bit of data. So let's use this, and I don't really need to save this on the self object. Let's just say command equals read a line and strip out any new space from there. So let's delete that. So we'll just say read a line of input from the socket. And for now, maybe let's print out, say received, and we'll put our command in there. It's a little format string. And then let's just delete the rest, because the rest of it was like sending a response back. But for now, let's just have it print out what it received here. So, okay, so that's cool. Now I need to do a little bit of setup. So right here, I need to create this TCP server instance. So let's do that in our code. So maybe at the start of our script here, we'll say setup our GPIO, and then below that we'll say setup our socket server, and then we'll say main loop listening for button presses. Okay, so let's create our socket server. So we'll say, okay, our server, and I don't need to use this prefix because I've imported everything from the socket server module. And again, so it takes the host and the port. And so in this case, we'll put a little define up here. So we'll say about server host. Yeah, I'll do this. And for this, I'm going to do 0.0.0.0. So this is just a little special thing. Like in their example code, they actually use localhost. The 0.0.0.0, this just means listen from any network connection. So if something running on the Pi connects to it, which would be like localhost, it'll listen for that. Or if something from outside of the Raspberry Pi, like my ESP board, tries to connect to this, then listen to that. So it's just a subtle little thing. You know, in most cases, when I'm writing a server, I want it to listen for any kind of a connection, either internal from the Pi or external from some other client. So that's what I want to use there. And let's put our server host in here. And then server port I've already got defined. So let's do server port again. Support 5000. Now I need to give my class name, and I rename that to LED handler. So let's do that. Okay, so now let's do that. And then now you need to call this server.serveForever. And you know, you might be a little worried at this point. So let's see what happens when I do this. So I'm going to call that server.serveForever, and let's run our Python 3 code again. So we'll do Python 3 server.py. And okay, so now it's running. And let's see, let's try. So for my ESP, I'm going to press the button here. And this is cool. So we see like received B toggle LED. And you see this B because, like I mentioned before, this is a raw byte string, because sockets are basically sending and receiving bytes. And this ESP board is sending ASCII bytes. And Python 3, you know, strings in Python 3 are Unicode by default, but it doesn't know that this socket connection is Unicode data. You know, it just knows that it's raw bytes. And so that's why I get back a raw byte string here. Whereas like if you did this in Python 2, you would actually just get toggle LED back and you wouldn't see a byte string like this. So again, it's something, and hopefully as I use Python 3 more, because I'm not as familiar with text in Python 3 as I should be. So it's something that they fixed or changed a lot in Python 3. So, you know, it's good. We'll kind of learn together as we go with this. But I mean, this is cool. So my server is working, like my handle code is getting called here. So, you know, we're printing out, we received that text. But let's see what happens. I'm going to press this button on the Pi, and uh-oh, nothing's happening here. So you might have noticed the problem here is that this serve forever function is doing exactly what it says. It's serving forever, and it's not returning after this. So my whole main loop is not running. And that's by design. So, you know, basically my server, like behind the scenes, something needs to be listening to this socket connection and waiting for a client to connect. And then once the client connects, creating this LED handler and calling that handle function. And that doesn't just magically happen in the background. You know, this serve forever function has a loop inside of it that's doing this forever. Now there are a few ways to kind of deal with this, because I want to do two things at once. You know, I want it to listen for these connections, and then I also want my main loop to run to deal with these button presses. So, you know, there are lots of ways you can deal with this. The Python APIs, the socket server, it actually has a function you can call, let's see, I believe that it's called handle request. And so you can call this function. So I could put handle request calls into my main loop here. And then that basically would mean, like, you know, I can handle the request at the start of my loop, then check my buttons and, you know, deal with their state. But the issue is that handle request takes some time. Like it actually has, I think, a little bit of a timeout in it where it's waiting for a user to connect. And that can mess up my main loop, because my main loop is, you know, assuming that most of the time it's going to be sleeping, waiting for my buttons to change state. And the rest of these commands happen pretty quickly. But if I throw in a command at the top that's, you know, handling my requests, and if that command takes a long time, when I press that button press might happen while it's inside of that handle request function, and I'm going to miss that button press. And that's exactly what I first started. I tried is, you know, I added the handle request and it wasn't responsive. And so the issue is that, you know, it takes a little bit longer than my main loop can deal with. So I think the best way to deal with this is to use an extra thread. Where basically, you know, I can have something running in the background, like this serve forever function. It can go do its thing in the background, and then in the foreground thread, or the main kind of thread here, my main loop can run. And because the Pi is pretty fast and has multiple cores, you know, both these things are kind of running at once, in the sense that, you know, my main loop is going to run, and then at the same time, the code that's listening for sockets is going to run. And it's not super hard to switch to threading here to do multi-threading. I've done this in a lot of other streams. So we just want to import the threading module from Python, and then we want to create a thread to actually run this serve forever function. So let's create a server thread object, and this is going to be a threading.thread object. And then every thread has to take a target function. So this is the code that's going to run when the thread starts. And the nice thing is I can actually just give it my server.serveForever function. So it's going to call this function when it starts. So, okay, so that's good. So now I don't need to really call it here. Now I do need to do a little more setup. I'm going to set this as server thread.daemon equals true. So I've talked about this before. Basically, there's a daemon mode for threads, which means that this thread, if daemon mode is true, it won't stop the program from exiting. If my main loop stops for some reason, then this background thread is just going to die. It'll just finish. If this is false, which is the default, this thread would actually block my program from stopping. And I need some way for my background thread here to know, like, oh, my main thread finished, I better stop too, which gets pretty complex to send messages between threads like that. So, really, because this background thread isn't that important, I want it to run whenever my program runs. And if my program stops for some reason, I want my background thread to stop too. So that's why I set the daemon or the daemon mode to true on there. And then I just basically need to do server thread.start. And so now that's going to actually kick off, and it's going to call this server.serveForever target function in the background. And that's going to go run in its own thread behind the scenes here. Now I'm going to do one little extra thing that's not immediately obvious, but I'm going to import the @exit library. And so this is a nice little library. Again, Python, batteries included, and they do all kinds of things for you. I'm going to do this @exit.register. So this will register a function to be called whenever my program ends. So like if I press Control-C and that throws a keyboard interrupt exception, it's going to make sure that this function is called. I could put this in a try finally block, but I sometimes like to use this @exit because it's a little bit cleaner. I don't have to pollute the rest of my code with this. But I want to call on my server object, there's a shutdown function that Python has. So if you look at this, you can see this shutdown function, and this tells the serve forever loop to stop, and it'll wait until it does. And the reason I want to do this is that, when that server thread is running, it opens a listening socket on port 5000, the server port. And if I immediately quit my program, if I press Control-C, because this is a background thread, it's not going to gracefully shut down. It's just, boom, it's done, it's dead. It doesn't have a chance to do any shutdown code. And, because these sockets are sort of global in the sense that like two processes can't be listening on the exact same socket, I might leave things in a bad state where my code ran, it opened that socket, but then because it effectively crashed or just quit very abruptly, it didn't close that socket connection. And the operating system is still thinking that, oh, that old process must still be listening, or someone's using port 5000. And if I try and run my program again, it actually will fail. It'll say I can't bind to that port. It's in use already. And there's a timeout. I think like after 4 minutes or something, the operating system realizes like, oh wait, this is some kind of a zombie socket, that no one's actually using, and then I can go back and run it. But just to be smart, I'm going to add this @exit register to call the server.shutdown function. So now, whenever my script exits for any reason, it's going to call server shutdown. That's going to signal my server object to gracefully close its socket connection. So it'll do the right thing and clean up. And that'll just prevent issues so that if I run the script, stop it, run it again really quickly, it's not going to immediately fail. So, okay, so let's try this now. Let's run our script. And okay, so I got something wrong here. So let's see. TCP has no attribute serve forever. Where did I get this wrong here? So I created my thread and I gave it a target. Oh, so I have a misspelling mistake. See, I was about to dive in and start troubleshooting stuff, but luckily I caught that. So okay, so serve forever. Now, okay, so now our code's running. So let's go back. So on my ESP, I'm going to press the button. And okay, this is cool. So we received toggle LED. That's all good. Now on my Pi, let's press the button and let's see what happens. So hey, look at that. Button pressed, LED turned on, toggle again. So obviously both things are running at the same time, which is exactly what I wanted. So I've got my background thread that's running my socket server class. So when I press the button on the ESP, it's receiving it and printing out the toggle LED. And then my main kind of loop that's checking for the button logic, that's also running in the foreground thread. And that's, sending out the socket events there. So that's awesome. Everything's working exactly how I want. So we're pretty darn close to finishing this up and making this work. So now I just need to toggle my LED, which is very similar to how I did it in the Arduino world. So let's do, so I want to do a little check. I want to see, did I get that toggle LED command? So if command equals, and again, I need to use a byte string, because if I just did a string in Python 3, it's actually going to be Unicode, and it's not going to be the same comparing a Unicode string to just a string of bytes that the socket received. So I want to do that byte string. Now if I receive toggle LED, then I want to run some code here. So let's do gpio.output, and then on my LED pin, and oh, actually I need to set up my LED. So let's add some LED pin state up here. That's pin 18, and I also need to set up my LED as an input. So let's do setup LED pin as gpio.out, and let's turn the LED off whenever it starts up. So we'll say gpio.output LED pin gpio.low, so that'll turn it off. Okay, so now I want to do whenever I get the toggle LED, output on the LED pin, and just like in the Arduino code, you can actually do a read, a digital read on this, and then invert the value, so use the not operator. And so I want to do gpio.input LED pin, and so this is going to read, you know, what's the current state of the LED, flip it around, and then set the LED to the new value there. And then let's just also put it in else, and just print, you know, unknown command. Just in case this check up here fails for some reason, I'll at least know, because it should print out unknown command here. So okay, let's save this and let's run our server and let's see what happens. Now you get this little warning. This is just an annoying thing about the RPI Gpio library, where basically like it registers for inputs the little like change listeners, and you know, if you don't do proper cleanup, you get these errors. It's annoying that you kind of have to add this boilerplate code where you say, okay, disable this warning. I don't really care. So I'll do that right after I set up the GPIO mode here. So we set it to false, but it doesn't affect our program. Everything else should be running. So okay, so now let's see. I'm going to press the button on the ESP side, and look at that. The LED turned on the Pi, and we actually see. So you know, we're still receiving the same toggle LED byte string, but it looks like it's, you know, it's doing what we want here. So I can press these. I can toggle the LED on the ESP, toggle these, and you can pretty much do these at the same time. You know, in reality, like you saw in the ESP8266 code, you know, when I get a button press, that happens first, and then when I receive data, that happens right after that. So, you know, these things, the ESP runs so quickly that you can effectively kind of, you know, feels like you're doing both these things at once in your code here. So, you know, I think that's pretty much it. So it's just kind of neat to kind of demo these a little more and see, you know, this is basically a bare minimum example of having both the ESP8266 and the Raspberry Pi sending and receiving commands with each other. And, you know, just to go back to the code, you can see this is not that crazy of code. Like, you know, there's probably some new stuff if you haven't done a lot of socket programming here. There's some new functions and things to learn. But we've created in, let's see, 55 lines of code, a server that listens for commands and toggles an LED, while at the same time listening for button presses and sending to another device a toggle command there. So that's pretty cool, and that's showing off a lot of the power of Python, in that it has all these nice little high-level helper classes here. So okay, so if folks have questions, throw them into the chat, and I'll see if I can answer them real quick. So let's jump back to the main view. And like I said before, look in the description below. You'll see links to the GitHub repository with the code for this example, links to the previous two videos, and I'm thinking I'll probably have another video again next week on Friday in this series, and we'll probably wrap it up. And I'm thinking about, you know, what topics could I do there. You know, maybe we might play with looking at the Mqtt protocol. So it's a neat little protocol for devices to talk to each other, and there's some Arduino libraries that you can use that are pretty easy to talk Mqtt. And then on our Raspberry Pi, we can actually, there's some real simple little Mqtt servers. So that's something I'm thinking about. We might try that next week for this. So, okay, so let's see if there are any questions in here. Let's see, what do you think about Circuit Playground to feather M0 Wi-Fi to Adafruit IO? Yeah, that would totally work. So you could have a a circuit playground talking to a Feather M0 Wi-Fi board, you'd need to use like a serial connection probably, because the circuit playground only has I2C and serial outputs exposed, and serial is going to be the easiest. You can do I2C communication between two Arduinos, but it gets a little weird, a little funky. I think serial is easier. But yeah, you could totally do that and use that as a bridge. But you could, I don't see any reason why not. If you had a I2C Wi-Fi board or a serial Wi-Fi board, which I don't know of any offhand, but maybe the circuit playground could directly talk to a Wi-Fi thing. So that's that. Does the spawn socket thread die upon each connect request? So good question. So I think you kind of mean like in the code here. So like the background thread, when someone connects to it, it's going to run your handler code, and then what happens after that? And actually, it will keep listening. So the socket server class is built to listen for as many connections. Like until you tell it the server shut down, it's always going to be listening for connections. Now the default socket server that I'm using here doesn't use multi-threading, so that if two things tried to connect to my board at the same time, only one of them is going to win. And that's okay, because like my processing is pretty quick and fast here. Like I read a line and I check and see what happens, and then it's done. So in some cases that second connection could just be queued up and waiting for this handler to finish. And then once the first socket finishes, then my second socket runs and it does the same thing. But if you look at the documentation for socket server, they mention you can actually do this. They have this forking or threading mix-in, where it's a little more complicated, but you basically change how you create the TCP server class, where it can actually spawn a new thread or a new process in the background every time a connect request comes in. And in that way, it can handle multiple requests at the same time. Each one gets its own little thread to do its own thing there. So it's a good kind of point in that, like right now, it's maybe not the best at handling a lot of different concurrent connections, but it isn't bad, because as long as this processing is pretty quick in my handle function, then you're never really going to notice that, lots of things are queued up and waiting to run inside of here. So let's see. And I think that would be, I think that's it as far as questions go. So yeah, on one, have you bridged Mosquito to Adafruit.io yet? No, I haven't tried that. So Mosquito is an MQTT server that Raspberry Pi and all kinds of platforms can run. And in theory, it is possible to bridge it to another MQTT server. I remember the configuration for MQTT, for Mosquito rather, you can define like a parent MQTT server, so that whenever your little local Mosquito server receives data, it can pass it up to, I don't think they call it a parent, but it can pass it up to another MQTT server. And because Adafruit.io implements an MQTT interface, you could actually have, a local server send data to Adafruit.io. The one tricky thing is that the path, when you connect to Adafruit.io's MQTT server, you kind of have to put in like your your username, I think, is part of the path, and like the topics that you subscribe to might not necessarily map to the topics that you want to subscribe to on your Mosquito client. But yeah, interesting thing. Maybe in a future kind of video project might look at doing something like that. So I think that's it for the questions. So I'm going to wrap it up. Thanks a lot for watching. Subscribe to youtube.com/Adafruit. You can watch this video and all kinds of other fun videos and projects. Subscribe to twitch.tv/Adafruit. You can watch me stream this stuff live. And then, also throughout the week, we've got all kinds of other shows and stuff going on. There's Desk of Lady Ada. There's the Layer by Layer by Noah and Pedro. So all kinds of cool live and pre-recorded content you can find on Adafruit's Twitch, YouTube, Facebook video now, which I want to start trying that out, but just need to see if I have the bandwidth for it. So yeah, that's what we're up to. Like, comment, subscribe, let us know that this stuff is useful and that you're getting a lot of value out of it, and we'll keep doing it. So this is Tony from Adafruit. Oh, and by the way, the next stream, so I stream a couple times a week. Mondays I like to do a stream to look at some interesting Pi software. This Monday I think I'm going to look at something called Pi Shift. That's a neat little project I just saw mentioned, where basically it turns a Raspberry Pi Zero into a USB drive that you can copy Python code to, and then it'll just run that code, whatever you copy onto it. So I wanted to try it out, see how it works, because it could be a neat little kind of beginner way to use. Like, you don't have to set up an SSH connection and copy files around. So look for that Monday. I'll do a stream. And then every Friday I do a longer, in-depth live stream like this one. And so next week we'll do part 4 in the Wi-Fi Raspberry Pi Talking to Wi-Fi Things series, which I think will be the last one. I think 4 parts seems like a good kind of length for series. Maybe let me know in the comments if you think it's too many, too little. But yeah, so we'll do a 4th one. And like I said, I'm kind of thinking maybe we'll do something with MQTT in the next one, just to really show, like, you know, we started with simple socket programming, just using netcat. Here's an example in this video of using Python socket servers, and then let's look at, you know, more real-world protocols of, like, you know, devices talking to devices using MQTT. So that's it. Tony from Adafruit. You know, I'll see you guys on Monday, and then Friday again for the next Wi-Fi Raspberry Pi Talking to Wi-Fi Things series. So see you.